Hello, everyone. Good afternoon or good morning, depending on where you are stationed right now. This is Jeff Prosise from Wintellect, and we're going to spend the next hour and a half or so together learning about a subject that excites me greatly these days, a subject that is occupying a lot of my time. That subject is deep learning. I've got lots of stuff to tell you about, lots of demos to share and code to share and stuff like that. And one of the things I'll do at the end of the presentation is share a GitHub URL with you so that you can go to a public repo I've set up and download all of the code samples I'm going to show, as well as a bunch that I'm not going to show. The fact that you're here probably means that you're familiar with our company, Wintellect, but just in case you're not, we celebrated our 20th anniversary a couple of months ago. We help companies build software. We help them keep their developers trained up on the latest and greatest technologies, and in general, just have a whole lot of fun doing what we do. So without further ado, let's get started. I have a lot of stuff to share here and want to make sure that we can get through as much of this as we possibly can. So why do we care about deep learning? Why do you care about it? And why do I care about it? Simply put, deep learning allows us to do things in software that were difficult or impossible just a few short years ago. Now, I often say the same thing about machine learning, and it turns out deep learning is a subset of machine learning. But deep learning goes further, making more magic possible, if you will, than classical machine learning does. For example, in this slide here, you see a picture of my son's dog. Her name is Lady. I put that up there because suppose someone at work challenged you to write an app that could look at a photo and determine whether or not that photo contains a picture of a dog, or perhaps a cat or something else. A traditional algorithmic approach to that problem isn't going to work very well. You may be able to write some code that will look at this particular photo and say, yeah, there's a dog in there. But then I guarantee that if you're approaching this problem algorithmically, I can throw you another photo with another dog, and it's going to foil your algorithm. With deep learning, we can actually build software that exceeds a human's ability to look at a photo and determine whether there's a dog in it. But there's much, much more than that. It's because of deep learning, for example, that real-time speech translation from one language to another and speech to text and text to speech have come so far in recent years. There are a lot of different computer vision problems also that we can solve with deep learning. For example, maybe you work at a company that manufactures something and you want to write software that looks at photos of parts coming off of an assembly line, and you want to identify which of those parts might be defective so they can be flagged for closer inspection. A few years ago, that was a difficult problem to solve, not impossible, but difficult. Today, thanks to deep learning and computer vision, it's a fairly easy problem to solve. And even that problem comes in a lot of variations. I had a gentleman approach me recently and say, hey, I need to write some code that will examine millions of images looking for a particular logo in it. And by the way, it has to work no matter what size the logo is, how the logo is colored, how it's oriented in the image, etc. Is there a way to do that? Yes, the way to do it is with deep learning, and we'll look at some examples along those lines here shortly. Another example, we had a customer approach us a year ago as part of a document management system that they wanted. They wanted us to help them write code or write it for them that could sift through millions of scanned documents and identify those documents that had redactions in them so that the customer could then flag those documents for review by a human. Again, that would have been a difficult app to write a few years ago. Today, thanks to deep learning, it and a lot of other things are relatively easy once you know how to do it. So let's start with a little bit of context. Deep learning is a subset of machine learning. But whereas classical machine learning relies on statistical learning algorithms like linear regression, logistic regression, support vector machines, and things like that, Deep learning does not. Deep learning is performed almost exclusively with neural networks. So in fact, what we're going to do in this hour and a half together today is take a deep dive into neural networks that allow us to implement deep learning. Uh, just to clear up a point of confusion, today when most people use the term AI, they really are referring to deep learning. Technically, however, artificial intelligence is bigger than machine learning and deep learning. So it's easy to confuse the two terms. Technically, artificial intelligence involves more than just machine learning and deep learning. But remember, when you talk to people who have been reading articles about AI or have been hearing about it, when they talk about AI, they are almost certainly talking about deep learning achieved with neural networks. So we're going to start with the basics. What is a neural network and why are neural networks so important in solving the kinds of software problems that sometimes are not solvable by other means? Well, a traditional neural network is put together like the one you see here. It is composed of neurons, which basically pass numbers from left to right in the network. In this example, we have a three-layer neural network. There's an input layer that contains two neurons. That means that whatever this network is designed to compute, we're going to have to give it two inputs, two floating point numbers in order to launch a calculation. It has one output layer containing a single neuron. That's the one on the right. Because there's just one neuron in that output layer, that implies that the purpose of this neural network is to output a number. Maybe it's designed to add two numbers or multiply two numbers or raise one input to the power of the other or something like that. Again, because there's one neuron in the output layer, that means there's going to be one floating point number that is output each time this neural network is run. In between the input layer on the left and the output layer on the right, you have a hidden layer. Now, state-of-the-art neural networks today sometimes contain hundreds of hidden layers. And whereas this hidden layer contains just three neurons, state-of-the-art neural networks sometimes today contain tens of thousands of neurons or even more. In other words, state-of-the-art neural networks that work some of the magic that we're going to look at can be quite a bit larger and more sophisticated than this. But regardless of how deep the network is, how many hidden layers there are, or regardless of how wide it is, how many neurons there are in the individual layers, they all work exactly the same way. One of the things I want to show you before we look at how to build the neural network or what kinds of problems we can solve with it is how these neural networks work. So I'm going to step through a series of slides that demonstrates exactly how they work, and that'll provide a foundation for everything that you ever do with neural networks. Just to lay the groundwork for a little bit of that. Basically, a neural network works because the neurons in these layers, by the way, are sometimes called fully connected layers. Each neuron in one layer is connected to each neuron in the previous layer and in the next layer. And each neuron is assigned a value. That value is arrived at by multiplying the values of all of the neurons in the previous layer by the weights that are assigned to the paths or the arrows that connect those neurons together, and adding a bias term. Each neuron has its own bias term. It's represented by B right here. So we are literally, when we execute a neural network, we're just taking some values in the input layer, doing some multiplication, some addition, then a little bit more addition, and we're propagating those values through the network. One thing that's interesting, and you'll see this in this first example I show you, is that one of the important elements of any neural network today is something called an activation function. You'll notice that when we propagate a value from the neuron labeled to Z over to the neuron that it's connected to in the output layer, we don't just multiply the value of that neuron by the weight, W3, and shoot that value over. Instead, we pass the value of that neuron multiplied by the weight through an activation function. Now, there are several popular activation functions. The one that you see used the most often in hidden layers in a neural network today is the one called ReLU, which stands for rectified linear units. All it really does is raise negative numbers to 0 while doing nothing with positive numbers. You'll see an example of that in just a moment. One of the things that you should realize about neural networks is how important these activation functions are. In math, there's a theorem called the universal approximation theorem. And that theorem basically says that you can approximate any function, whether it's linear or nonlinear, by summing the inputs of a series of linear functions and adding nonlinearity by running those sums through an activation function. In short, if it weren't for activation functions, neural networks would be able to handle linear mathematical problems for us very well, but they wouldn't be able to handle nonlinear problems very well, which means they wouldn't be very useful, because in the real world, almost all of the problems that we deal with in data, whether it's looking at an image to determine whether there's a dog in it or translating from English to German, involves highly nonlinear data. Now, that may seem a little bit abstract right there, so let's make this a lot more concrete. Here is what a neural network looks like. It's the same one you saw in the previous slide, where we have 2 neurons in the input layer, 1 neuron in the output layer, and we have a hidden layer consisting of 3 neurons. Each of those neurons in the hidden layer and the output layer is assigned a bias. It's just a little floating point number. It's typically fairly close to 0, but not always. The reason it's called bias, by the way, if you think back to high school geometry and the equation of a line, y equals mx plus b, where m is the slope of the line and b is the y-intercept, we can also say that b is the bias. The bias assigned to each neuron basically gives us the mathematical capability to take the slope, if you will, that's coming in from the neurons on the left, and to move it up or down by adding or subtracting a bias. So we see weights connecting each of the neurons to one another. We see biases assigned to the individual neurons. And when you read about neural networks and how they work, it may not go any further than this. I don't know about you, but being an engineer myself, things have to be a little bit more tangible to me. So let's make them more tangible. I trained a neural network exactly like the one you see here to add 2 numbers together, to add 2 and 2, or add 3 and 4, or whatever you want to add. And after training the network, I pulled out all of the weights and biases and added them to this figure. So you can see the actual weights connecting those neurons together. You can see that they tend to be values between -1 and 1, although that's not a strict requirement. And you can see the biases that are assigned to each of the neurons. Now, let's see how this thing actually adds numbers together. I'm going to start by assigning the values 2 and 2 to the 2 input neurons. So if all of this works, when we propagate the values through the network, we hope to see the number 4 or something very close to it as the value of the neuron in the output layer. So let's start propagating the values. First, we'll compute a value for the top neuron in the hidden layer by taking the values of the 2 neurons connected to it, multiplying those values by the weights of the paths connecting them, and adding the bias that's assigned to that neuron. That means we get a value of 4.03 for that particular neuron. Now we do the exact same thing for the second neuron in the hidden layer and for the third neuron in the hidden layer. Then we propagate those values over to the output neuron. Again, it's just simple math, multiplying values times weights, summing them up, and adding a bias. But there is one more thing at play here. Notice the activation function, where before that value 4.03 in the top neuron, for example, is propagated down to the neuron in the output layer, we run it through a function, so it becomes the max of 0 or 4.03. That means that it's actually 4.03 that is propagated down through there. But look at the neuron, the second neuron in the hidden layer. Max 0, negative 1.83 evaluates to 0. So that effectively means that nothing, that is 0, is propagated from that middle neuron over to the output neuron. The good news is, if you do the math here, and you can check my math if you want to, we do find that this network knows that the sum of 2 and 2 is 4. And here is a recap of how the values were propagated, multiplied by weights, had biases added to them, and then were run through activation functions when they propagated further. And I've grayed out this value right here to sort of highlight the fact that the activation function zeroed that out. Again, we came up with the right answer. The sum of 2 and 2 is 4. Now, here's something that's really important to know. Those weights and those biases are not unique. In fact, there's an infinite number of combinations of weights and biases for a given neural network that will accomplish what that neural network was trained to do. In fact, I trained this same neural network again, and I came up with a completely different set of weights and biases. And yet, if you repeat that procedure, starting with the input values and propagating through the network, you'll find that the sum of 2 and 2 is still 4. Now, all of the numbers that were computed in between are very different. There are different values right here, for example, but the output is the same. And again, I want to reemphasize that. There's nothing magic about these weights and biases in that there's only one way to initialize them. There's an infinite number of ways. And one of the things you'll find as you train neural networks is because there's a lot of randomness built in, randomness in how the data is shuffled, randomness in how the weights and biases are initialized. If you train it 100 times, you'll get 100 different sets of weights and biases, but that's okay. You typically don't care what those weights and biases are. You just care that they give you the right outcome. By the way, would this network be smart enough to do more than add 2 and 2? Could it add other numbers? Well, let's try it. In this example, I've changed the values of those neurons in the input layer from 2 and 2 to 3 and 5. I've done the same computations I did before to compute the values of the various neurons as the data propagates through the network. And if I check over on the right-hand side, the value assigned to the output neuron is 8. It looks like this is working because indeed the sum of 3 and 5 is 8. That is how neural networks work. There's nothing difficult about it. In fact, it's relatively simple. It's addition and subtraction in simple functions. Now, how do you come up with those weights and biases? That's a much more complex subject. The weights and biases are established when you train the network, and I'm going to show you how we train these neural networks. In fact, we're going to look at lots of examples, all of which train neural networks. I'm not going to say too much about how we arrive at the weights and biases. I'll say a little bit. That's where the math does get a little bit more complex. It's where you start learning about things like stochastic gradient descent and backpropagation and learning rates and variable learning rates versus fixed learning rates and optimizers and loss functions. The bottom line is, if you're not studying for a PhD in AI, you probably don't need to dive too deeply into how those weights and biases are arrived at. As a software developer, where your job is to understand what the state of the art is and apply that to solving business problems, what you care about is how you write the code that does the training and then assessing the results to make sure that the model you built is as accurate as you want it to be. How do you build a neural network? There are lots and lots of different libraries for doing it. You can build them by hand, by the way. In fact, it's a useful exercise to do once or twice if you're in grad school or you really want to understand how they work. But in practice, nobody builds these things by hand. We use libraries to do it. And there are a number of popular libraries out there, almost all of them free and open source. Arguably, the most popular one today is TensorFlow, which originally came from Google. One of the nice things about TensorFlow is in addition to having a Python interface, it also has a C++ interface. Probably second in popularity would either be Keras or PyTorch. PyTorch was developed by Facebook and it was put out there, it was open source so that anybody could use it. Keras is also open source. Its author now works for Google. So even though Google doesn't own Keras, they do have some influence over it, just like they do TensorFlow. Some of the other libraries are interesting. Apache MXNet is used some. Caffe and Theano used to be pretty popular. They're becoming less popular today. Same with the Microsoft Cognitive Toolkit, or CNTK. So it really doesn't matter which one you pick. You will find probably that with TensorFlow, Keras, and probably PyTorch, you'll find the best community support. You'll find answers to your questions on sites like Stack Overflow. You'll find good documentation for those libraries, etc. One of the nice things about Keras, by the way, is it uses other libraries for its back end. It defaults to TensorFlow. So when you build a neural network in Python using Keras, what you're actually producing is a TensorFlow network. And that's really cool because it makes the coding of neural networks much simpler. What you can do in 10 lines of Keras might require 50 to 100 lines in TensorFlow, which is why today even TensorFlow recommends that you not program TensorFlow natively unless you have a compelling reason to do it. Instead, you use Keras as an abstraction. That's why all of the examples I show you, I'm going to be using Keras under the hood. What it's actually doing is using TensorFlow to work its magic. Now, the beauty of Keras, besides the fact that it's free and open source, is that there are great books on it. There's great documentation out there and lots of answers to a lot of questions on popular sites like Stack Overflow. Another nice thing about it, it truly does abstract it out so that you can build sophisticated neural networks with a few lines of code. And rather than concentrate on all the little details regarding loss functions and activation functions and all that, you can focus on what really makes your network unique. So here's an example. This is a simple but entirely functional neural network coded up in Keras. You begin by calling Keras a sequential function. That's the first step in defining a sequential set of layers that comprise a neural network. Then you call add on that sequential object. In this example, I'm adding 2 hidden layers of 16 neurons each, followed by an output layer that contains 1 neuron. So again, there are 2 hidden layers here, 16 neurons each. The fact that I have 1 neuron in the output implies that this is going to be a network that does some sort of regression problem. It's designed to produce a single numeric output. Notice that in my dense layers there, we use the activation attribute to specify what activation function should be used to transform values propagated from that neuron to neurons in layers to the right. ReLU is an abbreviation for rectified linear units. It is probably the most popular activation function today, at least outside of output layers, so it's always where you start when you're building a neural network. Once you've defined the network, you call compile on that sequential object. What's interesting is not much happens when you call compile. It's not really compiling anything, and it's certainly not training the network. What the compile method really does is allows you to specify parameters that are going to govern how this network trains. You specify the loss function. Here I'm using mean absolute error. The loss function is how during training, Keras will measure the error between what the output should have been and what output it got in this training pass, so that it can go back and make adjustments to those weights and biases. The optimizer, in this case, I've specified Atom. That's one of about 10 or 12 optimizers that Keras provides. It is the optimizer's job to take the output from the loss function and figure out how to adjust the weights and balances in the network so that on the next training pass, the error gets smaller rather than larger. And we'll talk a little bit more about that process in just a moment. Once I've defined the network, then to train it, I call fit on it. Now, if you're familiar with scikit-learn, this is the same method you call on a model in scikit in order to train a machine learning model, to fit a model to the data, if you will. Keras uses the same terminology because it's already familiar to a lot of people who do machine learning. When I call fit, I pass in my X and Y, typically those are NumPy arrays of training data and the outcomes or the results for each row in the training data. I also specify the number of epochs, the number of times I want all of the training data run through the network. Typically, the higher the number of epochs, the more accuracy you will get, although at some point it will plateau. And I'll show you in a moment how we decide what the right number of epochs is. We also specify the batch size. The batch size says to Keras, in this case, batch size equals 128, that rather than run one row of data through the network, compute the loss, and then go back and adjust the weights and biases, I want you to batch that up. I want you to run 128 rows of data through the network, sum up all of the losses, and then go back and adjust the weights and the biases. A larger batch size will mean the network trains faster. Sometimes, not always, but sometimes the network will be a little bit more accurate with smaller batch sizes. But a batch size of 1, which Keras would not complain about, unless you're dealing with a very small data set, would probably take that network forever to train. When you call fit, there are a couple of attributes that you can specify that are very useful. One of them is called validation split. The other is called validation data. If you've done machine learning before, you know that it's one thing to train a model, but it really does you no good unless you can measure how accurate that model is. When you call fit in Keras, if you include a validation split equals 0.2 parameter, you're asking Keras to take 20% of the data set that you're training with, that is 20% of the X's and Y's on the left, and separate that out for testing so that basically in each epoch or each training pass, 80% of the data will be used for training and 20% of it will be used to assess how well the training went. If you don't want Keras to do the split for you, then you can use the validation data parameter instead, and you can explicitly provide references to your own test data that you've split off. It's not uncommon for us to use scikit's train test split function to do this, by the way, but either works. But in virtually all cases, you want to use one of those two parameters because otherwise you don't know how accurate your network is. You can't really tell how well the accuracy is progressing as you train through multiple epochs, etc. So before I look at the first example or show it to you, I want to mention this. As you've seen, how a neural network works once we've arrived at the right weights and balances is very simple. The hard part, the complicated part, the reason people get PhDs in neural networks is because of what's called the backpropagation part of the training. That is, once we've run a batch of data through the network, we've computed a loss with a loss function, how do we go backwards through the network and adjust all of those weights and biases so that we get a better result in the next training pass? And then in the training pass after that, and the training pass after that. Essentially what happens is what I described earlier. For each batch, a loss is computed. The optimizer, whether it's Atom or another one, decides which direction to manipulate the weights and biases further back in the network and how much to manipulate them, and it adjusts them prior to the next training pass. So there's a lot of complexity there, a lot of math, but when you call fit in Keras, all of that is done for you. Excuse me. Now, I want to show you an example in just a couple of minutes. But one thing I want to emphasize, and this is something you're going to see in most of my examples, is when you train this network, it is important to provide validation data to the fit method, whether it's your own validation data or a portion of the training data set that you've let Keras split off through the validation split parameter. Otherwise, you don't know whether you need to train it for 10 epochs or 500 epochs or 5,000 or what have you. So what we typically do, and you'll see this in my examples, is when we call fit, we provide either a reference to validation data or validation split. we take the history object returned by fit, and we use matplotlib to plot the training accuracy and the validation accuracy over time, that is per epoch. And what we look for is a graph like the one you see on the lower right, where here it appears that once we got to about epoch 35 or 36 or so, we really did not need to train it any further because neither training accuracy nor validation accuracy was improving after that. So in this case, if I had originally trained it for 100 epochs, I may go back in the future and shorten that to 40 or 50 to shorten my training time, knowing that unless I make big changes to the network, those extra epochs are really not very useful. Once you have a model trained that you built with Keras, remember you call fit to do the training, how do you make a prediction with it? How do you run it? How do you give it the inputs and get an output? You call the predict method just like you do in scikit. With Keras, which remember is building on top of TensorFlow, what you input to it is an array of floating points, a NumPy array of floating points. So if the network expects 2 floating point values as input, this is exactly how we would run that trained network and use it to get an output. Let me pop over here to my browser and show you your first neural network. So I'm going to show you a lot of different examples here. And again, I'll give you a link at the end so you can download all of these and more. But I'm running all of these in Jupyter Notebooks hosted in Azure. It's a free service called Azure Notebooks, which is unfortunately going away. But Azure Notebooks is not the only way to run Jupyter Notebooks. You can run them locally on your machine. You can go over to Google Colabs and run them for free or whatever you want to do. These notebooks here should run in any notebook environment. I just happen to be using Azure Notebooks. So let me show you how I generated those weights and biases in the slides a few moments ago. It was pretty simple. Here's what I did. I just created a little data set with some random integers I came up with and the sum of those integers. So 3 plus 0 is 3, 4 plus 1 is 5, and so on. And then I split that into a set of inputs like the 0, 0, and a set of outputs right here. Then I did the same to generate a data frame for testing. Once more, each row here has 2 numbers followed by the sum of those numbers. Then in Keras, I created a sequential model. I used this line of code to create a hidden layer containing 3 neurons. Notice input dim equals 2. That's how it knows how many neurons should be in that input layer, and an output layer consisting of 1 neuron. In the call to compile, I specified mean absolute error as the loss function. Again, it's one of a handful of loss functions Keras gives you. Atom is the optimizer. One of the nice things about Atom is rather than use a fixed learning rate, it will actually vary the learning rate in an intelligent way over time to try to give you a good balance between reduced training time and increased accuracy of the training itself. Before training the network, I called get weights on the model. That's how I extracted those weights for the slide. This shows me the weights and biases that are assigned to the neurons and to the paths that connect them. And right now, they're basically just random numbers. But I then train the network. I call fit on it, passing in the training data that I created up top and the validation data that I created up top as well. I arbitrarily chose 500 epochs. I am setting batch size to 1 just because I want to, because I have such a small amount of data to begin with. Obviously, these are very small data sets. It's just 10 rows for training and 5 rows for testing. So I set the batch size to 1. And when I train that, and it takes probably just takes a few seconds because it's such a simple network. Notice that I've captured here from my call to fit the history object that fit returns. I then do something essentially identical to what I showed you in the slides to use that history object to plot the training and validation accuracy. And I see that right around epoch 100, the validation accuracy bottoms out. So unless I change the architecture of the network, it's not going to get any better no matter how many epochs I train for. And if I train this thing again, I'll probably decrease it to 150 or 200 epochs, because after that, nothing is really happening that's useful. I then call get weights on the network again. This is how I got the weights that I put in the slide. Now, these are different ones. Every time I run this, I get different ones. But remember that in the first call to get weights, I'm just getting the random numbers that Keras assigned to the connections and to the biases. The second call to get weights, which takes place after training, I'm seeing the trained weights and biases. But then the proof of the pudding is, what if I use this network to make predictions? Remember, its goal is to add two numbers together. So I call predict with a NumPy array containing the values 2 and 2, and the network tells me that the sum of those two is 3.998574, which is not too bad. It's not exact, by the way, and note that neural networks don't deal with integers. They deal with floating point numbers. But since you're never going to design a neural network just to add two numbers, you're going to design it to do much more sophisticated things. You can see that this thing works. So that's a very simple neural network, but it is entirely functional. We're able to look into it and see what weights and biases were assigned before and after training occurs, and then we can call predict on it in order to have it do predictions. So that's just a start. There's a lot more to talk about, but it's an important start in helping you understand what these neural networks are and how they work. Now, let's get a little bit more real world. In practice, it is more common to use neural networks to perform classification than it is to perform regression. That is, it's more common to have them make predictions that involve possible output classes than it is to just predict numbers. As in machine learning, there are two types of classification. There are binary classification problems and multi-class classification problems. A great example of binary classification is you look at an email. Is it spam or is it not spam? You look at a photo of a defective of a part coming off an assembly line. Is that part defective or is it not? Those are binary classification problems. Multi-class classification simply means that we have more than two possible outputs. If you're doing optical character recognition, for example, to OCR handwritten digits 0 through 9, that's a multi-class classification problem because there are 10 possible outputs, the digit 0, the digit 1, etc. So I'll show you examples of both of those, but first let me show you in Keras how you define a network that does binary classification rather than one that does regression. And I've highlighted the differences here in yellow from our previous example so that you can see that. When we're building a binary classifier as a neural network, we make sure that the output layer contains one neuron and that its activation function is sigmoid. Sigmoid uses the equation you see in the upper right corner. It basically squashes values down to between in a nonlinear way so that the output falls between 0 and 1. In effect, in a binary classifier, the output value will be the probability that the input represents a given class. Let's take a look here at how we make a prediction with a binary classification network once we have it trained. Once more, we call predict and we input a NumPy array with all the values. Then we actually get an array of arrays back, and if you want to get the computed probability, you get it as I'm showing here. But also, when you're using a neural network to do classification, you can also call the model's predict classes method. Maybe you've trained this network to indicate whether an email is spam or not spam. If you simply want to know, did the network classify it as spam or did it not, you can call predict classes. If you want to know the probability that it classified it as spam, then you call predict rather than predict classes. And I'll show you an example of that. Let's go back to my browser for just a moment here. And I want to go over to another example. This one, uses a fairly famous data set, the Titanic data set, to demonstrate binary classification with neural networks. Now, this data set, if you're not familiar with it, it's real information from the voyage in which the Titanic sunk. That information includes information about all 800 or so passengers who were on board the Titanic that night, including their passenger ID, whether they survived. 0 means they did not, 1 means they did. The fare class that they were in, that's first, second, or third class, their name, their gender, their age, and a few other things. So what I want to do here is, rather than build a classical machine learning model that will predict whether someone will survive the sinking of the Titanic, I want to do that with the neural network to see how we do binary classification with the neural network. So I first do a little bit of work. I'm just learning more about the data set here, finding out how many rows are in it, how many of them might contain missing values. You want to somehow fix that either by removing rows with missing values or imputing values for the missing values in a neural network, just like you do in traditional machine learning. And in fact, it's arguably even more important in a neural network because neural networks don't really know what to do with not a number. So I then do a little bit of feature engineering. The main thing I'm doing is I'm dropping columns from the data set that really have no bearing on the outcome, like the passenger's name or their passenger ID. I'm also right here one-hot encoding the values in the sex column and the P-class column. Hopefully you're familiar with one-hot encoding. It's the same thing here it is in machine learning, and it's just as important to neural networks as it is to conventional machine learning models. That is, they don't know how to deal with text strings like male and female. They do know how to deal with numbers. So one-hot encoding is a way to take a column of categorical data with strings like male and female and turn them into columns of ones and zeros. All I've got here are a bunch of ones and zeros. Neural networks can deal with that very well. Let's see here. One more thing I do, just as an aside, is if you look at this data set, we've got lots and lots of ones and zeros in these columns, but in the age column, we have values that are much higher. The network would probably train okay if I didn't do anything about that. Although, in fact, if you try it, you'll find it doesn't train quite as well. With neural networks, even more than conventional machine learning models, normalization of the data is important. If you can get every column so that all the values are between 0 and 1, there's a good chance the network is going to train better and possibly be more accurate as well. Here, this column definitely contains values that are much larger than values over here. So I use scikit's standard scalar class to normalize the values in the age column. If you're familiar with standard scalar, rather than just quashing the values down so that they're between 0 and 1, we transform all the values so that the mean of all the values in the column is 0, and there's a standard deviation of 1. This scales the numbers down in an intelligent way so that they're on approximately the same scale as those one-hot encoded columns of zeros and ones. Then comes the fun part. We define a neural network. Here I have 2 hidden layers of 32 neurons each, once more using rectified linear units for the activation function. Because it is a binary classification problem, I use binary cross entropy as my loss function and sigmoid as my activation function in the output layer. I'm also doing something here that I haven't mentioned to you yet. I'm adding dropout. One of the issues that you always are concerned about in machine learning is the model overfitting the data? Is it learning the training data too well? If so, it may seem that you've built a very accurate model, but in fact, it's not going to generalize well. It may not be that accurate and probably won't be when you present it with data it's never seen before. The same problems with overfitting that apply to conventional machine learning models apply to neural networks as well. And one of the ways that we attack that in neural networks is we add dropout layers. In this case, in each epoch, each training epoch, 25% of the connections between the neurons in this layer and the neuron in this layer will be randomly dropped. That means it has the effect of preventing the network from learning the training data so well that it's not going to generalize well. And this is a very important and very common technique that data scientists use when they train neural networks to increase generalization, or another way of saying it is to decrease the chance of overfitting. By the way, you never know going in whether you need dropout or not, or how much. You never really know how many layers is the right number of layers, or how many neurons is the right number of neurons. There's a lot of trial and error involved, even for credentialed data scientists who do that for a living. By the way, notice the input dim equals 6 here. I'm saying that the input layer should have 6 neurons, and you'll see what those inputs are in just a moment. So we define the network we call fit with the data that we split off from the original data set for training and the 20% that we set aside for testing. We're going to go with a batch size of 20 and 20 epochs. We do the training. As usual, we plot the training and validation accuracy, and we see that up here, by the time we've gotten through 10 epochs, it looks like we were peaking out with a validation accuracy of around 0.8, and it wasn't really getting any better. So we basically have a network that should be about 80% accurate in predicting whether a passenger on the Titanic will survive or not. So let's run it to see what it tells us. So what is, for example, the probability that a 30-year-old female traveling in first class on the Titanic will survive the voyage? Well, here we create a NumPy array of the 6 inputs for that input layer. We pass that NumPy array to the model's predict method, and because it's a sigmoid output, we get back a value between 0 and 1 representing a probability. This tells us that according to our network, there's a 95% probability that a 30-year-old female who traveled in first class on the Titanic will survive. But what about a 60-year-old male in third class? Look at that. Looks like that person is much likely to survive, which is why when you travel on big ocean going ships, you always want to be in first class. It also helps to be young and female if you can. Of course, I'm being a little bit facetious there. But there is an example of binary classification with a neural network. Now, let me build on that just a little bit before we move on to multi-class classification. One of the things that we're often asked to do in machine learning these days is deal with text. For example, build a model, whether it's a traditional ML model or a neural network that classifies emails as spam or not spam, or that performs sentiment analysis on reviews, takes the text of a review on Yelp or something published through Twitter, and assigns it a number from 0 to 1, indicating how negative or positive the sentiment expressed in that text is. That's something marketing departments like to use these days, so that they can get a heads up if say tweets that target their company suddenly turn negative. So if you're familiar with working with text in classic machine learning, you know that somehow the text has to be vectorized before it can be used in a machine learning model. It can't be just characters, it needs to be turned into numbers. The same is true with neural networks. All they know how to deal with is floating point numbers. So somehow, if we're going to build models that do spam classification or sentiment analysis on text strings, we need to know how to vectorize that text so that a neural network can do something with it. Now, here's one way to do it. Keras gives us a class named tokenizer, which will, quote, tokenize text strings. Another way of saying that is vectorize text strings. So take a look at this example where I have 2 simple text strings, quick brown fox and jumps over lazy dog. I can create a tokenizer in Keras. I can call its fit on text methods, pass in that array of text strings, and that produces a vocabulary. It's basically a dictionary of all of the words that were encountered in the training text, along with an index. Then I call text to matrix on the tokenizer to produce basically a one-hot encoded version of that. If there were 50,000 different words in my corpus of training text, this would be a sparse matrix with 50,000 columns, mostly zeros, but with ones where the corresponding words appear in the documents that I trained with. Now, that's exactly how we tend to vectorize text for use in classic machine learning models. And while you could do that with a neural network, you'll probably find that that neural network won't train very well. We typically use a slightly different approach to vectorizing text for neural networks. Let me go back a slide. Instead of calling text to matrix to produce that sparse matrix of ones and zeros as you see here, instead I call tokenizers text to sequences. What this does is it produces a much less sparse matrix. Here, rather than simply have lots and lots of zeros and a one indicating that certain word appears there, we put the index of that word in that column in that row. What this tends to do is it produces a slightly denser or a less sparse matrix, which helps that neural network do what it's designed to do. So instead of just creating pure vectors as we do in classical machine learning, we tend to use these text sequences with neural networks. Then when we define the neural network, we include an embedding layer in the network. I won't go too deeply into what an embedding layer does. There's a lot out there in the literature, but basically it takes those sequences that we produce from the training text and it converts them into very dense vectors in which there's actually semantic meaning, in which there is recognition, for example, that the words king and queen are related, whereas the words dog and sailboat are not related. There would be more distance between them in the word embedding vector space. This is key, however, to dealing with text with the neural network. If my goal is to do, say, spam classification, classify an email as spam or not spam, then that will be a binary classification model. Therefore, I will have one neuron in my output layer with a sigmoid activation. Remember, that gives me a probability from 0 to 1 as an output and binary cross entropy as my loss function. Let's look at a quick example of that. How would you do sentiment analysis, for example, using a neural network? Well, here's how I might do it. What I'm doing in this example is I'm loading one of the data sets that's built into Keras. It's the Internet Movie Database data set, which contains, I believe, 50,000 movie reviews, each individually scored with a 0 or 1, 0 indicating it's a negative review, 1 indicating it's a positive review. Now, there are other data sets I could have used here, but the fact that Keras builds this one in as a sample data set, just like scikit-learn does with a lot of sample data sets, makes it easier for me to experiment with this. Then down here, I do the vectorization. I didn't have to do the vectorization because when I loaded the IMDb data set, the text had already been vectorized, it had already been tokenized. I do need to turn it into sequences of equal length that can be fed into an embedding layer in my neural network. So here's the network. We start with an embedding layer. We flatten the output out. It's a multi-dimensional NumPy array coming out of the embedding layer, but we need to flatten that out into a one-dimensional array prior to going into the first dense layer, hence the call to flatten. You can see my sigmoid output here. And then basically, when I call fit, I train the model as usual. I plot the validation accuracy and the training accuracy, and it looks like within pretty quickly, just a few epochs, we peak out in validation accuracy around probably 85 to 88%, something like that. If we want to see how this model actually performs, we would do that by asking it to score some text strings for sentiment. So I defined a little function here that does some preparation on the text before we pass it into the model. It removes punctuation symbols, remove numbers and things like that, converts everything to lowercase. Then I call that function and it says, easily the most stellar experience I've ever had is a very positive comment. It scores 0.93, where 0 means negative, 1 means positive. On the other hand, the long lines and poor customer service really turned me off, which I think we would all agree is a very negative comment, scored only a 0.04. Now, again, there's nothing that requires a neural network here. You can do this same thing with ordinary machine learning, but this is how you would do it with a neural network. You can see that it works pretty well. And in a moment, we're going to start looking at some things you can do with neural networks that you can't really accomplish, at least not easily, using traditional machine learning. So, hope this is making sense so far. And assuming it is, let's move on another step and talk about multi-class classification. What if you wanted to build a neural network that does facial recognition, something that neural networks tend to be pretty good at, by the way? We're going to look at an example shortly. In that case, maybe there are 100 different people belonging to the faces you've trained it with. So when you input a face, you want it to tell you which one of those people that face most likely belongs to. Since there are 100 different people you trained with, it becomes a multi-class classification problem. Notice this. The output layer in a neural network that does multi-class classification should have one neuron for each possible output class. If this were a facial recognition model that had been trained to recognize 100 different people, then I would change this number 10 right here to 100. And notice the activation function. It's not sigmoid, it is softmax. What that does in a multi-class classification problem is this. If I have 10 neurons in the output layer, each of those neurons will give me the computed probability that the input belongs to each of the 10 possible classes. In other words, all the values of the neurons in that softmax layer will add up to 1. And obviously, the neuron that has the highest value is the one that corresponds to the predicted class, the person that this face belongs to. Once you have the network trained, you call predict on it as usual to make a prediction. Or if you're not interested in the probability so much as you are in what was the predicted class or classes, then you can call the predict classes method on the model just as you can for a binary classification problem. So let's look at an example or two here. In fact, I may take time to do more than an example or two because I've got some really fun stuff to show here. So one of the early machine learning models that was built and operationalized a few decades ago was one that allowed the US Postal Service to scan handwritten zip codes on an envelope and to recognize what digits each of those handwritten digits represented. We can duplicate that today pretty easily using logistic regression or some other common learning algorithm in a classic machine learning model. We can also easily duplicate that using a neural network. So what we're going to do here is build and train a neural network that will take scans of the handwritten digits 0 through 9 and tell us with a high degree of accuracy which digit a given scan represents. Because there are 10 digits 0 through 9, this is a multi-class classification problem. And once more, I'm going to leverage a data set that's built into Keras. It's a famous data set called the MNIST data set. It contains, I believe, 70,000 scanned handwritten digits 0 through 9. And you see it in a lot of examples. It's a great one to experiment with, whether you're building neural networks or playing with scikit, learning to do classic machine learning. So I first load the sample data set right here from Keras, prevents me from having to go out and find it and load it manually. This is what one of the scanned digits looks like. You can see that it's a two-dimensional NumPy array. It's just a bunch of pixel values essentially from 0 to 255. That would make more sense if instead of looking at raw numbers, we use matplotlib to plot that. So that number that we just looked at is actually this, which appears to be a handwritten 5 and a fairly sloppy one at that. In fact, Let's go a little bit further here, and we're plotting the first 50 of the tens and thousands of scanned handwritten digits in that data set. You can look at these and you can tell what the digits are. You can also see there's quite a lot of variation between the way the same digit is drawn. These were drawn by different people, different grad students. We do a little work here just to find out how balanced our data set is. As in any machine learning problem, when you're doing classification, you want a data set that is as balanced as possible, that is, has an approximately equal number of representations of every possible class. And it looks like here, we have a relatively balanced data set. I then define my neural network. Because it's a multi-class classification problem, we right here set the loss function, categorical cross entropy. We use softmax as the activation function in the output layer. And because there are 10 possible outputs, we make sure there are 10 neurons in that softmax output layer. I arbitrarily chose to include just one hidden layer and the number of neurons inside it just to see how that would come out. So before we do the training, we have to do a little bit of work. Remember that in the data set, there's a column specifying what digit all those pixel values correspond to, a 0 for the digit 0, a 1 for the digit 1, etc. But those need to be treated as categorical values. They need to be one-hot encoded. One way to do one-hot encoding in Keras is to call Keras' own two-categorical method. So I'm taking the training labels, the 0, 1, 2, etc., in the rightmost column specifying what digit the scan corresponds to, and I'm one-hot encoding it into actually 10 different columns of ones and zeros. We also need to do a bit of reshaping on the input here so that it's compatible with the input layer in our hidden in our network. Remember, I said that the input shape here is 28. That's 28 by 28 pixels for each scan. I'm reshaping the data here so that it will fit into that neural network. And I'm doing some normalization by dividing all the numbers by 255. This means instead of asking my network to deal with values between 0 and 255, it's going to be dealing with floating point values between 0 and 1. And that actually does help it train better and converge faster and be more accurate. I then do the training. For this one, I trained for 10 epochs. It looks like it took about 16 seconds each, so not too bad. I plot the training and validation accuracy, and looks pretty good. Looks like I'm getting up to around 98% accuracy by the time I reach the 10th training epoch. And just to see if it really works here, I'm picking one of those images in the data set, converting it into a NumPy array here, and inputting it to the network to have it tell me what digit it thinks it is. Notice the call to predicted classes right here. It tells me, looks like it's a 2. But when I simply call predict rather than predict classes, remember there are 10 possible outcomes here. There are 10 neurons in the softmax output layer. This gives me the probability that the network believes that this input corresponds to each of the possible outputs. Notice it is almost dead certain, essentially 100% certain that that corresponds to a 2, where it is assigned incredibly low probabilities that that input represents any of the other integers. So not only did it get it right, it was very, very sure it was correct, and it was. Here's another example of multi-class classification. Let's do some facial recognition. Let's see how that works with neural networks. Now, we can do this to an extent with classic machine learning models using learning algorithms like support vector machines. But guess what? That is not as accurate as a neural network. So here's what we're going to do. We're going to load up a sample data set that comes with scikit. It's called the Labeled Faces in the Wild data set. It's a popular one. It's public domain, so anyone can use it, and it's often used in facial recognition models like this one. So we're loading it from scikit. We'll be building the model in Keras, but that's okay. We're getting the data from scikit. And here we find that there are 1,140 images that were loaded. We did filter these down some so that we're only loading images for the 5 people that appear in the database the most often, and that each image measures 62 by 47 pixels. We do a check for the balance. We actually see that George W. Bush is represented more than others. Not a huge deal. It probably just means the network is going to be better at identifying him than others. And then we use matplotlib to plot the first 24 images in this data set, just so we get an idea of what this neural network is going to be dealing with. We then do a little bit of reshaping on the data to get it formatted so that we can input it into a neural network. We do a train test split, that's from scikit, of course, to do a training and test split on the data, and then we start having fun. I'm going to start with the neural network that contains one hidden layer with 128 neurons. Notice it's a softmax output layer. Class count is 5, the number of different people represented in the phases I'm training with. So we're building a very simple but hopefully pretty effective neural network here. We do the fit, running it through 100 epochs. If we look at the validation and training accuracy over time, it looks like we get up to around 90% with the validation accuracy, which is not bad. Further down in this notebook, I'm experimenting by varying the network architecture, trying different numbers of layers, different number of neurons in the various layers, etc. What you find is that you cap out in all cases at around 90% accuracy. But that's not bad. We're going to do better momentarily. But with the neural network, we're able to easily get about 90% accuracy training on a facial data set like this one. And by the way, if you're familiar with confusion matrices, which are a really good way to see how accurate a classification model is, I generated a confusion matrix here, and it tells me that in testing, when this network was presented with images of Colin Powell's face, it got it right 45 times and wrong 5 times. With George W. Bush, it got it right 96 times and wrong a handful of other times. As you probably know, in a confusion matrix, what you want to see are big numbers along this horizontal, because that's where the network got it correct. You want to see zeros or small numbers outside of that, because those represent misses. And you can tell here that this network seems to do a pretty good job of identifying faces. By the way here, would dropout help some? In this notebook, if you want to download and play with yourself, I've got the same network with dropout added. You find that it doesn't make much of a difference, but one thing you might do, may not make a lot of difference, or it might. Try increasing dropout to say 0.3, 0.4, even 0.5 to help your model generalize, and see if that might get the validation accuracy a little bit higher. Let's see here. One more example, because this example is going to lead into some later examples that are going to be really fun. Actually, I don't want to get into that one yet. Let me put that off just a bit. So we've seen how to build a simple neural network that performs regression, that is, outputs a number. We've seen how to build neural networks that do binary classification, and how to build neural networks that do multi-class classification. One thing you should realize is that there are different types of neural networks. One of the most prominent types is the convolutional neural network, or CNN for short. Convolutional neural networks are what has revolutionized computer vision in recent years. It is how computers look at an image and identify objects in that image, like hot dogs, hamburgers, cats, pianos, guitars, and things like that. It's how state-of-the-art facial recognition is done. It's how virtually all computer vision problems are handled today. And ultimately, it's how you want to attack the problem. If you want to build that app that looks for defective parts coming off an assembly line, that looks for redacted documents in a document database, that scans millions of images looking for a company logo, the convolutional neural network is going to do that for you. What is a convolutional neural network? Over on the right, it has one or more fully connected layers, just traditional neurons like the ones you've seen so far. But preceding that, it has a succession of convolution layers and pooling layers. Let me go to the next slide to tell you a bit about what those are doing. If you've ever used Photoshop to blur an image or sharpen an image or do edge detection on an image, you may know that Photoshop uses something called convolution kernels. It's one of the secrets to image processing, where you look at the image as a 2x2 array or table of pixel values. You take a matrix called a convolution kernel, like the one you see right here, and you pass it over every pixel in the image. And for each pixel you pass it over, you multiply the pixel value under each square of this kernel by the value in that square. You sum up the inputs and you replace the value of the pixel in the center with that computed sum. Using a convolution kernel like this one here and running it over every pixel in this image above produces this right here. This is called an edge detection kernel, and this is the crux of how convolutional neural networks work. They take the images that you train them with or that you input to them, they run over them multiple convolution kernels, sometimes hundreds or thousands of them, so that they can learn to recognize the shapes that say this image contains a hot dog or this image contains a guitar or something like that. If I go back a slide, it's the convolution layers that do that edge detection. We call that feature extraction. In the pooling layer, we cut the image down to half of its original size, typically by subsampling. Then we run it through convolution kernels again. Then we cut the image down to size again. What this means is, as the image progresses through the network, initially we're looking essentially at micro features, but by the time we've subsampled that image down to maybe a 20th of its original size, we're looking at more macro features, like looking for the shape of a cat's head rather than the shape of a cat's eye. They work, and they work incredibly well. In fact, they work so well that today, convolutional neural networks can classify images more accurately than human beings can. Every year, there's a competition called the ImageNet competition, where research teams and really anyone who wants to compete to build a machine learning model that does image classification the most accurately. For a few years, we were cruising along. We couldn't get anywhere near 10% error. Humans are around 5%, by the way, until 2015, when Microsoft submitted a network that had been built by Microsoft Research in China called ResNet 152, which for the first time scored higher in image classification than human beings did. So these things truly have revolutionized the field of computer vision. And guess what? You can build a convolutional neural network in Keras. It makes it really easy. Here I'm defining a succession of convolutional layers followed by pooling layers to cut the image down to size. I'm using dropout to try to help the network generalize better. I'm using a classification layer consisting of 100 neurons and a softmax output layer, which implies that whatever images I'm classifying here, there are 10 possible outcomes in each of those neurons in the softmax output layer is going to give me the probability that the image I input into it corresponds to each of those 10 possible outcomes. So I want to show you an example, but first I want to mention another class in Keras that can be incredibly useful. It's called Image Data Generator, and although I don't have to use it in this next example I'm going to show you, I am using it. This is one of the ways that companies like Microsoft and Google and others train convolutional neural networks with millions and millions of images, far too many images to fit in memory at once. Image Data Generator in Keras basically removes the memory limitations and batches images up from the file system or from some other source so that you can train a neural network with theoretically an infinite number of images. It's really simple. You new up an image data generator object, you call its flow from directory method, and you point it to a path in the file system. The cool thing about this is Keras is willing to infer the class names from the directory hierarchy. So if you look in the lower right corner of this slide, looks like I have 3 sets of training images in this example. I have a set of hot dog images in a folder named hot dog, a set of pizza images in a folder named pizza, and a set of sushi images in a folder named sushi. Rather than manually label these images, because I've set the class mode to categorical in my call to flow from directory, Keras will automatically assign the label hot dog to all of the images in that directory, the label pizza to all of the images in the pizza directory, and so on. And although I'm not going to use it here, you should also know that Image Data Generator does something else really cool. It supports something called data augmentation. When state-of-the-art CNNs are trained, we typically train them not just with the images that we've accumulated for training, but with those same images transformed in various ways, rotated by 30 degrees, scaled up, scaled down, flipped around the horizontal or vertical axis. That helps the neural network recognize whatever object you're trying to get it to recognize, regardless of its size or orientation, rather than manually transform all of those images. I can ask Image Data Generator to do it for me using attributes like the one you see highlighted in yellow here. It's an easy way to multiply the number of training images you have at the expense of increased training time, of course, and often makes your convolutional neural network more accurate. Let's take a look here at an example or two. I'm going to go to this one now. So I want to build a neural network that does image classification. I want it to be able to look at a photo, tell me what the likelihood is that that photo contains a hot dog, what the likelihood is that it contains sushi, or what the likelihood is that it contains pizza. Now, remember, I'm using food items, but this generalizes to anything you want to do, to parts or defective parts, to dogs, cats, kittens, or whatever. You can train the network to do anything you want. So what I'm doing here is building a CNN from scratch. I've started off with Image Data Generator. I've got a bunch of training and testing images in the local file system. There are actually 60 images I'm training with and 30 that I'm testing with. There are 20 hot dog images, 20 pizza images, 20 sushi images for training, and 10 of each for testing. So I knew up an image data generator to serve those images up. Again, don't really need image data generator here, but if I were training with millions of images, I would. And then I'm using a matplotlib to show some of the images just so you get an idea of the nature of the images I'm training with and of the images that I'm testing with. Then I define a convolutional neural network. This one has 3 pairs of convolution and pooling layers. We flatten the output to feed into a classification layer. I'm being fairly aggressive about dropout here. And because I'm wanting it to classify each image that I feed into it as either hot dog, sushi, or pizza, or a combination of the 3, my softmax output layer has 3 neurons. So we do the training, and the training actually takes a while here. It looks like about 48 seconds per epoch. And I'm training for, let's see, how many epochs? 20 epochs, which is not too bad. Still, it takes this thing a while to train because guess what? It is very compute intensive. Each image that I train it with is being sliced and diced in the convolution kernels hundreds of times. In the end, when I look at the training and validation accuracy, I'm getting there, but it's not really acceptable. It looks like my validation accuracy is peaking out around 80%. Let me tell you what's going on here, and this is important. CNNs have absolutely revolutionized computer vision problems. But for most of us, training a CNN to be 96, 97% accurate requires more processing power than we can afford to throw at it. I could make this CNN here probably 95% or more accurate by training it with hundreds of thousands of food images. But guess what? Doing that on my desktop or my laptop, it could take months or even years. It is tech giants like Microsoft and Facebook and Google that build and train hugely sophisticated CNNs with millions and millions of images that set records and win competitions like you saw on the slide a few moments ago. Now, that doesn't mean that we're not going to benefit from CNNs, but I do want you to realize that yes, while you can build these CNNs in Keras, you'll probably find that it's not practical for you to do the training with enough images to make it accurate to be useful. By the way, how do the tech giants do the training? They do it on multiple on HPC clusters equipped with GPUs, graphical processing units, which parallelize the work they can do in some of these HPC and GPU clusters in hours or days, what would take years on a traditional laptop. So let's go a step further here. What about these CNNs? Well, guess what? Microsoft and Google and other organizations that build very sophisticated CNNs and train them also open source them so anyone can benefit from them. You and I can use the networks that these companies have already trained. And in fact, the networks that they publish have been trained on the ImageNet data set. That means these networks have been trained to recognize about 1,000 different objects that appear in an image, and they're typically trained with more than 10 million images each. Again, not something you and I can do unless we care to go spin up a GPU cluster in Azure and spend a few $100,000 to do it. But if you're Microsoft or Google, you can do it. By the way, this diagram right here depicts one of the early but very effective convolutional neural networks. It came out of the University of Oxford in England. It was called VGG16, and we're actually going to use it in an example here in just a moment. The good news is there are a lot of different trained CNNs that are included with Keras, so you don't even have to go out to GitHub and download them. Keras will download them for you. They even have pre-trained versions of Microsoft's award-winning ResNet network, which won the ImageNet competition back in 2015. So if I wanted to use one of these pre-trained convolutional neural networks in Keras, it can be this simple. Here I'm loading up the VGG16 network, initializing it with the ImageNet weights, in other words, the weights that allows it to identify about 1,000 different objects and images. Then I load an image from the file system, do some preparatory work on it to get it formatted and scaled the way VGG16 expects it, and I pass that image to predict. Then I look at the output. Let me just show you real quick what that looks like because it's kind of interesting. Here, I'm loading up that exact network, the VGG16 network. You can see it being loaded up right here. Here I'm showing all the layers that make up that network. Then I'm loading a hot dog image that I have sitting in my local file system. I'm preparing it in the way that VGG16 expects. By the way, this preprocess input function comes from Keras, and there's a different version of it for each different pre-trained network that Keras lets you load. And then when I ask it to do a prediction, it tells me it thinks there's a 100% chance there's a hot dog in that image, an almost infinitesimal chance there's a cheeseburger, French loaf, etc. It looks like VGG16 is very good at telling you whether an image contains a hot dog. I won't go into it too deeply, but when you download these notebooks yourself, if you care to see the feature maps that were generated from that image, you can actually reach into that VGG16 network and pull them out. Here are the feature maps generated by the convolution kernels. This is the first layer of them where the images are at full resolution. Here's the next layer where the images have been shot down to half their original size, then half their original size again, and half their original size again. You can see how, excuse me, the images seem to come a little bit more blurry because they're being subsampled down to half their size and half their size again and so on. But it allows the network to recognize what's in that image at various scales and resolutions. Now, I also loaded another preloaded network or pre-trained network, Microsoft's ResNet 50 v2, which is more accurate than VGG16. If you scroll through here, it has lots and lots of layers in it. Super sophisticated network. Would take, I don't know, decades, centuries of CPU time to train. I loaded the same image, prepare it, ask ResNet 50 to tell me what's in that image. It says there's a 99.87% chance there's a hot dog in it. It scores other possible objects as possible, but very low. But here's what's interesting. I fed into it a sushi image and asked ResNet 50 to classify it for me. It says there's about a 50-50 chance that image contains confectionery, 16% chance it contains conch, 8% chance it contains a croquet ball. What I can conclude from that, and it's correct, is that when this network was trained with the ImageNet data set, that data set included hot dogs. It did not include sushi. So it begs the question. So, okay, if it's not really feasible to train a CNN from scratch on my own without spending tons of money on Azure or AWS for GPU clusters, and I'm limited with these pre-trained networks to detecting things in an image that they have pre-trained them with, then what good is all of this? Well, the answer is this. And I'm going to go over about 5 minutes here. I hope you'll forgive me for that. If you need to go off to a meeting or something, feel free. But I think you're going to find this really interesting. Here is the holy grail of deep learning when it comes to computer vision. It is called transfer learning, and here's what it does. It lets you have the best of both worlds. It lets you take these super sophisticated, super accurate, pre-trained CNNs published by companies like Microsoft and Google and repurpose them with very little training time to recognize not what they were originally trained to recognize, but to recognize what you want them to recognize. Here is what transfer learning really does. Here is that VGG16 network that I loaded into Keras a few moments ago. All of those convolution and pooling layers form a part of the network that we refer to as the bottleneck layers, also known as the feature extraction layers. And out on the right-hand side, VGG16 has 2 layers of neurons, 4,096 neurons each, followed by a softmax output layer with 1,000 neurons, which allows the classification layers to take all those feature maps generated from the bottleneck layers and classify them in 1,000 different ways. What's the probability it contains a hot dog? What's the probability it contains a fish or a bicycle, etc.? With transfer learning, here's what we do. We load VGG16 or whatever pre-trained network we want to use, and we remove the classification layers. Then we append our own classification layers with the softmax output layer designed to provide probabilities for all the different classes we want to predict. And we train it up on the output from the bottleneck layers. Do you see what's happening here? Training a CNN like this is expensive because of all the processing that goes on in the convolution layers and the pooling layers. By using VGG16's bottleneck layers or some other networks layers and not retraining them, but simply saying, hey, if you see these features coming out of an image, this is what it represents with their own classification layers, we can get, in a lot of cases, extremely high classification accuracy with very little CPU time and as few, believe it or not, as a few dozen training images. How do we do that? Well, here's one way to do it in Keras. We load up VGG16 or whatever pre-trained network we want, and we use include top equals false to tell Keras to get rid of the network's built-in classification layers. Then look what I do. I iterate over all of the VGG16 layers that are left, setting their trainable property to false. That means even if I retrain this network, the weights assigned to those layers are frozen. That's going to speed the training time because that part of the network isn't having to be retrained. Then I define a network of my own that starts with the VGG16 bottleneck layers, followed by my own classification layers, then I train it just like I do any other network. Now, let me tell you this, that works, that is transfer learning, but it can be a little bit slow. Here's the way we really do it in practice. It's a little less intuitive, but it can be orders of magnitude faster. What we do is we load VGG16 or whatever pre-trained network we want without the classification layers. But rather than build our own model around it, we run all of our training images through that base model. And we use the output from the base model to train our own network. The only real difference here is we're not adding the VGG16 bottleneck layers to our own network. Same results, but this trains orders of magnitude faster. Why? Because when I use the technique that I showed you on the previous slide, even though the VGG16 layers that I brought in are not being retrained, for each epoch that I train it with, every image is being run through the base model and having its features abstracted. But those features extracted look the same every time because we've frozen those layers to training. Here, I'm optimizing things. I'm running all my training images through the base model one time to extract their features and then training my network on that. Again, about an order of magnitude faster, a little less intuitive, but it's the way we do it in practice. Let me show you one final example, and then I'll conclude and give you a URL where you can download these examples. Here is transfer learning. We're going to build an image classification network that does exactly what the one in the previous example did, that can tell me whether an image contains a hot dog, sushi, pizza, or some combination. We're going to use the same 60 training images and the same 30 testing images, but as you see, because of transfer learning, we're going to get a much more acceptable result. So I create my image pipeline pretty much as before around image data generator. I'm showing some of the training and testing images. Notice they look a little bit discolored. That's because I'm using Microsoft's ResNet 50 v2 network. And when I transform the images, when I pre-process them using ResNet 50 v2's pre-process input function, it converts them from RGB to BGR, which is why they look a little bit weird. You can still tell you're looking at hot dogs in this example. Then I run all of my training and test images through the base model to have their features extracted. Then create my own classification layer. Look, just 32 neurons here, very aggressive dropout, a softmax output layer with one neuron for each of the three possible classes that I'm looking for: hot dog, sushi, pizza, etc. And this thing trains almost instantly. It goes through 20 epochs in about 20 seconds. More importantly, look at this. I'm getting 90 to 95, even higher percent validation accuracy. Again, same number of training images, 60, not millions of them, but 60. Same number of testing images, 30. But I'm achieving very high classification accuracy, and training took almost no time at all. That is the power of transfer learning. And because of transfer learning, and because Microsoft and Google and others have been kind enough to spend millions of dollars building and training very sophisticated CNNs and letting us simply download them from GitHub and other places, you and I can build super sophisticated image classification models as well. And the final thing I'll say is this. I've done everything here in Python. Most neural networks are built in Python, although they can be built in other languages as well. A few weeks ago, I did a webinar on ML.NET, Microsoft's machine learning library for .NET developers. Inside ML.NET, sort of hidden away, is this amazing little method called load TensorFlow model. So I could quite easily, for example, take this network that I built and trained with Keras using transfer learning. Because Keras is using TensorFlow under the hood, I could save this out as a binary TensorFlow file. I could bring that binary file into my C# ML.NET project, and I could be, with a couple of lines of code, literally, I could be utilizing this network to look at images and tell me what those images contain. and it could be repurposed to do almost any image classification test, to look for redactions, to look for logos, to look for all sorts of other things. The possibilities are almost endless. So, and you're probably thinking, and yep, Jeff's talking is almost endless as well. So let's finish this up here. So here's the URL of a public GitHub repo I maintain. It contains all of the examples that I showed you here and some that I didn't show. Feel free to go there, pull these notebooks down, play with them all you want to, share them with friends and colleagues, share them with your family over dinner tonight. I'm sure they'll want to know everything you learned about deep learning today. And do check back in the repo from time to time, because I'm constantly posting new samples. I posted one new one this morning, and I'm constantly revising existing ones. So you'll most likely see cool new stuff show up there. So with that, I would suggest that we call it an afternoon. Let me go back to the opening slide. There's my email address, my Twitter handle. If you have questions, follow-ups, if there's anything we can help you with, any problems we can help you solve using machine learning or deep learning, feel free to reach out to me there, and I'd be happy to help you if I can. Thank you for attending today. Rachel, are you there? Do you want to say anything in closing, or should I just go ahead and wrap things up?
Yeah, I think that you could just go ahead and wrap things up. I don't see really, I see one question, actually. I can read that to you.
Sure.
It says, how can we use TensorFlow and Keras in C#.NET?
Yeah, the best way to use TensorFlow and Keras is to use Keras to build a model, save it as a TensorFlow model, then use in your C# project, add a reference to the ml.net NuGet package and call ml.net's load TensorFlow model, and then you can consume that model from C# the same way you consume it from Python. It's even possible to do transfer learning entirely in C#. Maybe we'll cover that in another webinar someday.
It looks like one more question.
Okay.
Do you have recommendations on books for a beginner on the subject?
Yeah, probably the best one is one called, let me pull it off my shelf to make sure I get it right. It's called Deep Learning with Python. The author's last name is Chollet, Chollet. He is the person who wrote Keras. He's still very active in its evolution and maintenance. He now works for Google. And of all the books on deep learning, especially with Keras, it is my favorite. So Deep Learning with Python, it comes from Manning Press, and the author is Chollet, Chollet.
Hey, it looks like that was the last question.
Well, Rachel, you know what that means? It means I've worn everybody out.
Yeah,
So,
it usually does, right?
yeah, you know the feeling, right? So,
Yeah.
folks, once more, let me thank you. In fact, all of us at Wintelect, thank you for giving us your time. I hope it's been helpful. I hope you learned something that you didn't know before. And if I can ever help you with anything, feel free to reach out to me. Thank you so much, and I hope you have a great rest of the day.